This is part one of the lecture for section 5.1 from Math 311, a course in linear algebra at Western Illinois University. So, new chapter, and it's all going to be about orthogonality and orthogonal sets and all their nice, really neat applications. So, before we go on, let's just visit some couple familiar concepts where we in R2 and R3. If we go into in R2, let's suppose we have two perpendicular lines in R2. So this is not the x and y axis. These are just two arbitrary lines that are orthogonal to each other, and they're intersecting at the origin. So in this case, if we let's say we know that any line through the origin is a one-dimensional subspace in R2. We can call this one. Let's say we call this line L, but we can also say it's W. So it's because this is a one-dimensional subspace in R2. Now we know we can project any if we take any vector v. We can arrange it so that v, of course, starts at the origin. And we know that we can project v onto a line, just onto this line using the projection formula, right? Okay, so we can see that we were able to show how we can write v, in fact, as the sum of two orthogonal vectors. We can write this vector, the projection, and this vector, which we calculated as v minus whatever this vector was. And we said that these are orthogonal. And well, what's more is that if we take this vector, we can move move vectors anywhere we want. And so we can just, if we remove this, consider this vector as an element as a vector in this line, which of course is also a subspace. These will be orthogonal. Obviously, we can see that this vector and this vector are orthogonal. And then what we've shown is that v can be written as, we can see that, first of all, any vector in this line is going to be orthogonal to any vector in this line. And, in fact, any vector in general in R2 can be written as a vector in this line plus a vector in this line, if we just move this over here. Okay, so we have this. There's nothing, in a sense, there's nothing new here. We've just said that this vector right here is in fact a vector of a subspace in which everything is orthogonal in this subspace to this subspace. Okay, that's what we're doing. Okay, with the projection. In R3, let me remind you that the subspaces in R3 are the lines that go through the origin and the planes going through the origin, as well as the origin in R3 itself. And that once again, it's possible, we can actually project we can take any arbitrary vector in R3, again, if we call this v. Remember how we were finding the distance between a point and a plane? The way we did that is we projected it onto on the normal vector. Okay, where the normal vector was and I should say here, in this case, we have a line. This line is supposed to be perpendicular to the plane. Okay, so this is supposed to be perpendicular to the plane. And what we have, what we can do is we were able to project v onto the normal vector, and once again. So we found out what this distance was. This vector right here was the projection of v onto the normal vector, and we use this to find the distance between this point and this point. But we can also see that we can subtract v minus this vector, and we get this vector in the plane. And so what we have is and this vector again can be, because the normal vector is supposed to be the direction vector of this line here. Okay, so again, if we let this plane be subspace W, we can take any vector in R3 and we can write it as the sum of something in W plus something in this line. If we call this W1, we can call this W2, and they're both subspaces. And we have everything in W1 is orthogonal to everything in W2, and in fact this V can be written as a sum of something in W1 plus something in W2, and of course these things are orthogonal. Okay. Now what we have given you an example of, here we projected the vector onto a line, here we projected it onto a plane. That's how we got this. Well, it turns out we can project any vector we want onto any subspace of Rn, and we can do this using this notion of orthogonality. We can we can write, given any subspace, we can find another subspace such that everything in these two subspaces are orthogonal to each other, and they actually will sort of span all of Rn. Okay, meaning that we can write any vector in Rn as the sum of something in W1 plus something in W2. Okay, we haven't defined exactly what this orthogonal subspace is, but we'll get there. So this is an example of two examples of orthogonal decomposition, and that's where we're going to go through in the next couple of sections. Okay, so we'll start with the definition. So a set of vectors in Rn is an orthogonal set if the dot product vi dot vj is equal to 0 for all I not equal to j. And in English, what this means is that any two distinct vectors in this set are orthogonal. Okay. So there's some very nice properties of orthogonal sets, and well, the most important property is that any orthogonal set of non-zero vectors is linearly independent. Okay. Well, that's kind of nice. We know that linear independence is nice. So how can we prove that? So why is this true? So let's suppose if the set V1 through Vk is orthogonal. Okay. And remember, how did we prove linear independence? We assume there's some linear combination of them equal to 0, and then we show that all the scalars have to be 0. And so we say A1 V1 plus a dot plus CK VK is equal to 0. All right, then, well, what we can do is we'd like to show that all the C's are 0. Let's take, so if I is any number between 1 and k, let's take the dot product of this, of both sides with vk, or rather vi. So let's take vi dot c1 v1 plus ck vk equals vi dot 0. Okay. All right. Now, by the linearity of the dot product, we can distribute this vi, and then we can pull out the scalar. So this will be c1 vi dot v1, and then the next term, which you don't see in here, would be c2 vi dot v2 dot 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 plus ck vi dot vk. And we know that because we're taking a dot product with the zero vector, that's always going to be 0. Okay. And then because these are all of these are going to be 0, except for except for the ith term, right? So what we get, everything goes away except for ci vi dot vi equals 0. Okay, which remember the dot product of a vector with itself is its length. So this is ci vi squared. Okay, so vi, the dot product of vi with itself is the length squared. And because vi is not 0, that means that ci has to be 0. Okay. So that means, so ci is equals 0 for all I. So that means C1, C2 through CK are 0. Okay. And we get linearly independence that way. Okay. So orthogonality implies linear independence. All right. Now, because of another nice property of orthogonal sets is that we can actually see that if we take something in the span of an orthogonal set, we can automatically read off what these coefficients are. So if something is a linear combination, these C's are actually they're determined. They're unique. Well, we know that they're unique anyway because we now know that these are linearly independent, so there can only be one representation there. But we can now actually compute what these coefficients are. So why do we have it? Why is Ci equal to this quotient of WVI over VI dot VI? Why is that? Same idea. Okay, we can take VI for both sides. So VI dot W is going to be VI dot C1 V1 dot plus CK VK. Okay, and again by the linearity of everything, after we distribute and pull out the coefficients, this is C1 VI dot V1 plus C2 VI dot V2 dot plus CK VI dot VK. And once again, all of these are going to be 0 except for one of them. Okay, and that's going to be where you get VI dot VI. So we get CI times VI dot VI. Okay, so this is equal to VI dot W equals this. Maybe I'll just write this down here so it's a little neater. Okay, and because we don't have to worry about this being 0 because we're already assuming that this is a set of non-zero vectors. Okay, so we can divide both sides by this, and so we get that Ci is going to be Vi dot W over Vi dot Vi, and we can just switch these around here, and that we get this. We can interchange the W into VI, and we get this. Okay, so that's why that's another nice consequence. Okay, things are not you can read off. So this will happen if now notice one other thing is that the span of these vectors is going to be it's a subspace, and we actually have is that this, because this is linearly independent, it will be a basis for whatever subspace the span of them is. So that leads us to the idea of an orthogonal basis. And orthogonal basis, I don't think I even have to write the definition, do I? It's just it's a basis that is orthogonal. Okay, duh. Okay, if I can say that. All right, it consists of just orthogonal vectors. So a couple of examples in R2, we can clearly see the dot product of these is 0. Okay, so this will be orthogonal. This is orthogonal. Okay, the dot product. One, by the way, with standard basis is also orthogonal. 1, 0, 0, 1, that's obviously orthogonal. And we can see that if we take an arbitrary something like a vector like 5, 6, and we want to see the what would the CIs be here? If we want to write 5, 6 as a linear combination, let's say, of these two vectors, well, we could probably do it, by trial and error or some other trick. But according to a formula, we can take the dot product of V if we let this play the role of W and this be the role of V1 and V2, so this would be 56.10 over 10.10, and you can see this will be 5 over 1, which is 5. We do the same thing with the second vector, 56.03 over 03.03. You can see that this, I think you can see we have enough room. This is going to be 18 over 9, which is 2. And sure enough, we get that 5 times 10 plus 2 times 03 is in fact 56. Okay, so we get that nice decomposition there. Okay, and you could do the same thing with this vector, this orthogonal basis. Actually, we've done that before in other examples. If we move on to R3, we can see that hopefully we can see that this is an orthogonal set. If we take these two, the dot product is going to be 1 minus 2 plus 1, that's 0. The dot product of these two will be 1 plus 0 minus 1, and the dot product of these two would be 1 plus 0 minus 1. So this is orthogonal. Okay, and because we have this is an R3, the dimension of R3 is 3. This means must be an orthogonal basis for R3. Okay, and let's say we wanted to write the vector, let's say 2, 3, 5, as a linear combination of these vectors. What we can do, we just do the same formula. Let's take the dot product of this with 1, negative 2, 1, divided by 1, negative 2, 1. Okay, and what will this be? This is 2 minus 6 plus 5. I believe that's 1, and this is 1 plus 2 plus, or 1 plus 2 squared plus 1. That's going to be 6. We do the same thing. 2, 3, 5. Dot product 1, 1, 1. 1, 1, 1. Dot 1, 1, 1. We get 2 plus 3 plus 5, that's 10 over 3, so it's 10 thirds. And then finally 2, 3, 5, dot 1, 0, negative 1, 1, 0, negative 1, dot 1, 0, negative 1. This is going to be 2 minus 5, that's negative 3 over 2 plus 0 plus 1, so that's 2, 3, negative 3 halves. So in fact, 1/6 times 1, negative 2, 1, plus 10 thirds times 1, 1, 1, minus 3 halves, 1, 0, negative 1, that's equal to 2, 3, 5. So you just have to do, if you play around with the fractions, you just have to do them carefully, and you'll see that this checks out. Okay, so this is actually a lot easier than writing that, trying to do this by, linear algebra, just, setting up a 3x3 system of equations and doing reduced row echelon form. When we have orthogonality, the solution just drops right out. So hopefully that's kind of cool, I think. Okay. Well, it turns out we can actually improve, in terms of the niceness of the orthogonal sets, we can actually improve them by making them orthonormal. Okay, so what is an orthonormal set? An orthonormal set is just an orthogonal set that consists of unit vectors. So it's just where every vector in the set has length 1. So in terms of the another definition, we would say this set is orthonormal if and only if the dot product of vi and vj is 0 if I is not equal to j, and 1 when I equals j. Okay, this first condition makes the set orthogonal. The next one makes it orthonormal. Make sure that all the vectors are unit vectors, have length 1. Now, in our previous example, these were all orthogonal, say, but not orthonormal. Okay, same thing up here, because this has length. This vector has length 3. These two vectors have length the square root of 2. This vector, you can see that these vectors none of these have length 1. But we can always fix this by computing the length and then just dividing by the length. Okay, so some examples. Well, first of all, the standard basis is orthonormal. Okay, the standard basis of R2, and in fact the standard basis of any of Rn is orthonormal. Okay. Okay. All right, but in this case, let's say we had for the next case, if we go back to our basis 1, 0, 0, 3, okay, the length of this vector is 3, so we can just divide by 3, and then divide by we can basically replace it with 0, 1, and that would be this one. So in general, you can get an orthonormal basis from an orthogonal basis by what we call normalizing each vector. And what we mean by that is dividing by the length. Or we could say multiplying by the reciprocal of its length. So, for example, if we take 1, 1, 1, negative 1, you can see that the length of both of these is the square root of 2, right? Because we get 1 squared plus 1 squared is 2. Take the square root. Okay. So this gives us, we take 1 over square root 2, 1 over square root 2. 1 over square root 2, negative 1 over square root 2. Okay, and you can check very quickly that the orthogonality is still there. Multiplying by a scalar doesn't change the orthogonality, and in fact we just now the length. If we take the length of this is 1/2 plus 1/2. That's 1. Okay. Same thing here. If we go to our other example where we had 1, negative 2, 1, 1, 1, 1, and 1, 0, negative 1, okay, here the length was the square root of 6, right? You have 1 squared plus negative 2 squared plus 1 squared, that's 6, take the square root. Here you got 1 squared plus 1 squared plus 1 squared, that's 3, take the square root. 1 squared plus negative 1 squared is 2, take the square root. Okay, so we can get an orthonormal set just by taking, in this case this would be 1 over square root 6, negative 2 over square root 6, 1 over square root 6, and 1 over square root 3, 1 over square root 3, 1 over square root 3, and 1 over square root 2, 0 over square root 2, 0, and negative 1 over square root 2. Okay. So it's very easy to get an orthonormal set from an orthogonal set if you don't mind working with square roots and dividing by something. Okay. All right. So because orthonormal is a sort of a special case of orthogonal, every orthonormal set is orthogonal, and every orthogonal set is linearly independent. So from our first fact, we get that every orthonormal set is also linearly independent. We can also see that that if we have an orthonormal set and if we take any vector in the span of these v's, then that can be written as a linear combination, and these coefficients are actually going to be given by w dot v1, w dot v2, and so on. And that's basically the proof of that really just comes directly from the proof of fact 2 is just that in this case the if this says orthonormal, then this is all these denominators are going to be equal to 1. So we get VI, so CI is just going to be VI.W or W.VI, right? So so CY just repeats proof of fact 2 and use the fact that VI.VI is 1, so that implies that CI is going to be W.VI over 1, which is just W.VI. Okay, and so that's what the C's are, and that gives us what this linear combination is. Okay, and because the CI's are determined, there's a unique value of the CI that depends on W. These CI's are going to be unique. Of course, we already know that they're unique because this is going to be linearly independent. So an orthonormal basis is a basis that is orthonormal. Again, duh. Okay. All in the previous examples, this gives us an orthonormal basis of R3. This gives us an orthonormal basis of R2. Okay, and in fact, whenever we have an orthogonal basis, we just do this calculation, do this normalizing process, and we'll get an orthonormal basis. Okay. Now, what's not trivial is that we're going to show that every subspace has a just 1 minute, please. Can I answer this? All right. So every subspace has an orthonormal basis, and we will do that next time. So see you then, or actually a little bit in the next section. So see you next time.